Good morning to all my student. So the subject that I will taught today is data structure and algorithm with the course code PCC AIML 301, and today's topic is searching algorithm. Myself, Dr. Bidesh Chakraborty, professor in the Department of Computer Science Engineering AIML, Wholly and Stop Technology. So first, I would like to discuss what is searching. So searching in computer science refers to the process of finding the location of a specific element or value within a data structure. Now, the data structure can be array, can be list, basically a linked list we are talking about, or it can be a database. So there are very basically there are two types of primitive searching algorithms that are in your syllabus. One is linear search and another one is binary search. And other than these two, there are a lot of searching algorithms like hashing, exponential search, interpolation search, Fibonacci search, and apart from that, we have BFS, DFS, A star search, and all. But as in your syllabus, you have linear search and binary search. So today's topic is basically on these two searching algorithms. So first one is what? Linear search. Now, linear search means what? It sequentially checks each element until the target is found. That means until the value that you want to search or the end of the data structure is reached. This is the basically the logic of linear search. And the binary search is what? Efficiently searches by dividing the data into two hubs, and it require the data to be sorted beforehand. That means the prerequisite of binary search is what? The list of the array must be sorted. Otherwise, we cannot perform binary search. Now, in linear search, so given an array, we have to search an element from the array. Let's come with an example. Suppose I want to search 20 and we have a list that contains 12, 5, 10, 15, 31, 20, 25, 2 and 40. So in the linear search algorithm, first the element that you want to search, that is 20 here, it will compare with the first element of the array. That means it will compare with 12. So 12 is not equals to 20. That's why next it will compare with 5, then it will compare with 10, then it will compare with 15, 31, and when it will compare with the element that is present in the fifth index location, that is 20, so it will just come out from the loop and it will give the output, yes, 20 is present in the fifth location of the array, in the fifth location of the array. Now, if I want to search 26 and as the 26 is not in the list, so it will be what? It will be an unsuccessful search, and that's why the output will be 26 is not present in the array. It's a very simple one. Now, this is the algorithm for linear search. Here, the parameters that we have considered: A, that is the base address of the array from where I want to search. N is the number of elements in the array, and the value is what? The value that you want to search. So in step 1, I have initialized I is equals to 0. I is what? I is a loop variable. Then I have set another variable flag is equals to 0. So if flag is equals to 1, if the value of flag is flipped from 0 to 1, it means the element that you want to search from the array is there in the list. But after doing all comparison, if the flag value holds the initial value, that is 0, that means you can say that the element that you want to search from the list is not present in the array. So in step 3, it's a loop and it repeats step 4. So in step 4, what I have written, if a of I is equals to val, then what I will do, I just set the position POS, it's a variable. That means where I have found the data that I want to search, and I just flip the value of flag, that is from 0 to 1, and it break. Break means what? It directly come out from the loop. And then if the value of flag is 0, it returns 0. Otherwise, it returns the position plus 1. position plus 1. What it means? It means suppose the element is in the fifth index, but normally if we want to search, normally you can see that the 20 is present in the sixth cell. If this is 1, 2, 3, 4, 5, 6 cell. So that's why I have written here position plus 1. Sorry. Now this is the complete code that I have written in C language, so that it will be very clear to you how we can implement this linear search. So initially what I have taken, I have defined some variables. I, it's a loop variable, n for number of elements in the array. Now ARR is the name of the array, and the maximum value that I can store in the array, that is 20. Similarly, result and key is the value that I want to search. So first what I did, entered the number of elements in the array. So the number of elements, it whatever it is, it may be, it must be less than or is equals to 20. That means as the size of the array is 20, so maximum 20 elements you can store there, not more than 20. You can store 15 elements, you can store 9 elements, you can store 13 elements, no issue, but you cannot store 21 or any number that is more than 20. Now this is the declaration, array declaration. After that you have to populate the array. So the next, what I have written, printf enter elements. So here this is the for loop for I is equals to 0, I less than the number of elements, that is n I plus plus, and within that I have written the scanf statement, where using that statement each and every iteration I will store the elements into the array. So this is all about the population of the array. And then I want to say, I want to write, I have written the element that you want to search from the list. Okay. So if our previous example, suppose 20. So here the value of key will be 20. And then I have written a user defined function. The name of the function is what? Search underscore linear, and it takes 3 parameters. One is the base address of the array, n is the number of elements in the array, and key is the element that I want to search. So this is your function definition. Here I have set flag is equals to 0, and same loop for I is equals to 0, I less than n I plus plus. Within that I have compared ARR I. So in the initial pass or in the first pass, the value of I is 0. That means ARR 0. It will compare with K. In the next iteration, ARR 1 will compare with K. K means what? K is the key that I want to search. Okay. Now say for any value, let's assume that when the value is 5, that means ARR 5 is same as K. If that, then POS the position will be what? 5, and I have defined flag. I have flipped the value of flag. Flag initially it was 0, now this is 1, and this is break. Break means what? It will immediately come out from the loop. And then I have written one condition. If flag not is equals to 0, it return POS, and this value comes here as the result. Okay. So if the result is 0, we can say that the search element is not in the list. Otherwise, the search element is what? Result plus 1. So you can write here POS plus 1, POS plus POS plus 1 also. If that, then here just you have to write only result instead of result plus 1. It's a very simple code. And here the time complexity analysis. So already I have told you that there are 3 ways. One is best case time complexity analysis, one is worst case time complexity analysis, and another one is average case time complexity analysis. So when best case occur for that particular problem, when the element being searched for is found at the first position. That means every time if I want to search an element from the list or from the array, and the element is present in the first position of the array, this is very rare. So if that, then you can say that the best case time complexity is order of 1, or it takes unit time. Worst case means what? When the element is at the last position. When the element is in the last position or not present in the array. So in our example, we want to search 26. 26 is not there. That means from first to last we have to compare. We have to compare all n elements with 26. This is the worst case. That means the element can be found in the last position or cannot in the list. If that, then you can say this is the worst case time complexity, that is order of n. And the element, if the element can be found from any position, maybe the second position, maybe the third position, maybe the second last, maybe the third last, whatever it is, these are all belongs to the average case. Suppose the element is present in the present in the half of the array. Okay, let's assume that we have 10 elements. Say the element is present in the fifth location or sixth location or seventh location. So it will be what? It will be either n by 2 or maybe the second last. That means n minus 1. Maybe the maybe the third last, n minus 2. So n minus 2, n minus 1, n by 2, these are all asymptotically same as n. So that's why the time complexity of linear search in worst case is order of n. In average case also this is order of n. But for best case, that is very rare. The element always is in the first position of the array. This is very rare. On that case only we can say the time complexity for the best case is order of n. Order of 1. Now next I will just jump from linear search to binary search. Now in binary search there is a prerequisite, and that prerequisite is not there in linear search. Now what is the prerequisite? The array must be sorted. The array must be sorted. That means if the array is unsorted, you cannot implement binary search unless you have to sort the array. Okay, so the elements of the array or in the array must be sorted, then only we can do binary search. So this is the prerequisite. Now here, what is the algorithm? How we can do it? First, compare the element that you want to search with the middle element. So the list is already sorted. Okay, and I have already got the mid element. So you know the index, initial index, lower index, you know the higher index. Based on that you can calculate the mid index. So A of mid is the element that is present in the mid element. That is in the middle element. So first, my objective is to compare the element that you want to search with the middle element. Let's come to the example. So the item or the element that I want to search, that is 23. And here the elements in the list are already in ascending order. The elements are 1, 5, 7, 8, 13, 19, 20, 23 and 29. So here A of mid is which one? 13. So first I will compare this 23 with 13. Now as 23 is greater than 13, that means if 23 is there in the list, 23 must be in the right side of the list. Must be in the right side means what? This part. This part. The elements are already sorted. So there is no chance for getting 23 in the left half. Left half elements are the elements that are less than 13. So 1, 5, 7, 8 all are less than 13. So there is no chance for getting 23 in the left half. So if the element is present in the array, so it must be present in the right side. Now 13 is not 23. So we'll consider this half. We'll consider the half that contains 90, 20, 23 and 29. Now again, within this sub problem, our first objective is to calculate the midpoint, and you have to track the mid element. So here the mid element is 20, and now I'll compare this 20 with 23. Again 20 is less than 23. That means if 23 is present in the list, it must be present the right side of 20. Right side of 20. Okay, and the third in the third iteration, here the elements that I want to are there in the list is what? 23 and 29, and here the mid element is 23. So you will found that 23. So if I use linear search here, there are so many comparison. say 1, 2, 3, 4, 5, 6, 7 and 8 comparison, and after 8 comparison you will get the result, yes, 23 is present in the 7th index. But for binary search, only 3 comparison is needed. So this is the advantage of binary search over linear search. Now, this is the iterative approach and recursive approach. Both I have written here. So first I will discuss the recursive approach. So here again, this is the function binary search. It returns integer, that means the value, and it takes the parameter, that is the base address of the array, the lower index, the upper or higher index, and the element that you want to search. Okay, now here I have first done what? I have calculated the midpoint. So mid is nothing but low plus high by 2. Then I will compare this k, that means the element that I want to search, with a mid. So if the search element is present, is same as the mid element, it returns mid. But if not, that means if k is less than a mid, if k means what? The search, the element that I want to search. So if k is less than a mid, then my searching zone will be what? The left side of the array. So that's why I have written again the recursive function, that is binary search a, the base address of the array, then the low, mid minus 1 and k. So mid minus 1 means what? Mid minus 1 is the higher index of the left part. Else means what? If your k is greater than a mid. If this, then our search space is different. Then on that time I will search in the right side of the array. So on that time the index will be what? Mid plus 1. This will be the lower index. Hi is the higher index and the element that you want to search. So this is the simple, very simple binary search recursive algorithm. Now come to the time complexity. So how we can define the time complexity? So if any problem is solved by recurrence relation, then first of all you have to determine the recurrence relation. Here I have written the recurrence relation T of n is equals to T of n by 2 plus c. What it signifies? T of n means what? Time to execute the problem of size n. T of n, time to execute the problem of size n. So I divide the problem into 2 sub-problems and I will follow either left half or right half, not both. This line is very, very important. I have divided the problem into 2 sub-problems, but I will concentrate, I will focus either left half or right half. That's why I have written T of n is equals to T of n by 2 plus c. Maybe in the next lecture, when I will discuss merge sort or quick sort on that time, the recurrence relation that I will discuss on that time, that will be T of n is equals to 2Tn by 2. Because after divide the problem into 2 sub-problem, we have to focus the left part as well as the right part. But here in binary search, we have to focus either left part or right part. So that's why only one T of n by 2 is being used here. Okay, so the recurrence relation is what? T of n is equals to T of n by 2 plus c. Now again, this T of n by 2 again can be divided into 2 parts of size n by 4, and again we have to consider either left or right. So if we divide n by 2 into 2 parts, it will be n by 4. So I have written just replace T of n by 2 by T of n by 4 plus c. Here this c is the constant. This constant is basically for dividing, because any division takes unit time. Similarly, in the next recursive call, it will be T of n by 2 to the power 3 plus 3c. After that, it will be T of n by 2 to the power 4 plus 4c. That means if the size of the list, initial list may be 64, each and every recursive call, the size will be getting half. That means 64. Then the next recursive call, it will be 32. Next recursive call, it will be 16. Then it's 8. Then 4. Then 2. That means once upon a time, it will be 1. And after that, you cannot divide the list further. Okay, so after kth recursive call, let's assume that the recurrence relation will be T of n is equals to T of n by 2 to the power k plus kc. Because initially it was n by 2, next n by 2 square, n by 2 to the power cube, n by 2 to the power 4. So after kth recursive call, it will be n by 2 to the power k. And once upon a time, the size will reduce to 1. Okay, so if n by 2 to the power k is equals to 1, then we can write n is equals to 2 to the power k. Taking binary log on both sides, we can write that, we can find that k is equals to log n. Put the value of k is equals to log n, because t of 1 will be constant, and if you put the value of k, that is log n, then you will have c dot log of n. Here c is also constant. So the time complexity of binary search is order of log n, but the time complexity of linear search was order of n. So this is the very basic difference between linear search and binary search. Again, I am saying you, there are no prerequisite for linear search. The elements may be sorted, may not. Whatever be the order the elements are present in the array, we can perform linear search, but that is not possible for binary search. For binary search, the list must be sorted. And next, the difference between linear search and binary search, this is very important. The derivation of the time complexity is also very important for your semester, and this is also a very important. What is the difference between linear search and binary search? So for the definition point of view, we can say that linear search is sequentially checks each element in the list, whereas binary search divides the list into two hubs to search efficiently. Searching method, in terms of searching method, starts from the first element and moves sequentially. And for binary search, repeatedly it divides the list into two halves. So this is the way the element in the list getting reduced by half. Precondition, there is no precondition for linear search. It works on unordered or sorted list, but for binary search, it requires the list to be sorted. The time complexity already I have said, for best case of linear search, though that is very rare, it's order of 1. In worst case and average case also, this is order of n. For binary search, again, the best case is what? If the element is the mid element. You have divided the list into two hubs based on the mid, and first recursive call, the element is present in the mid element. If that, it will be order of 1. Otherwise, for average case also, for worst case also, it will be order of log n. In terms of efficiency, linear search, obviously, it's less efficient for large database or large list, and for binary search, this is highly efficient for large database. Implementation complexity, linear search is very simple, easy to implement, but binary search is much more complex than linear search. User scenario, linear search is useful when the dataset is very small and obviously unsorted, and for binary search, this is preferred when the dataset is large and sorted. So this is all about today's lecture. Thank you.